Hello and welcome back. If you follow the channel, you know that we have been involved in a long-winded restoration of the Apollo communication hardware. We have been mainly focusing on the flying hardware in the command module, but the ground equipment is no less impressive. The relatively small power of the flown equipment was compensated for by very large antennas on the ground. Once the spacecraft was sufficiently far from the Earth, NASA used three 26 meters, that's 85 foot, antennas. One was at Goldstone in the California desert, one in Madrid, Spain, and one in Honeysuckle, Australia. They were about equidistant around the globe, so that one of them would always be able to see the spacecraft. These and a whole bunch of smaller ones were part of the so-called Manned Space Flight Network, or MSFN, and entirely dedicated to the Apollo program. In addition, each of the three antennas was supplemented by a nearby backup antenna belonging to NASA JPL. And on top of that, there were two monster 64 meter, that's 210 foot, antennas, one at Goldstone, California, and one in Parkes, Australia. The Goldstone one being really a military spy antenna in disguise, and the Parkes one a radio telescope. But both were borrowed by Apollo programs as backups and saved the day in numerous occasions. Finally, the whole thing was interconnected by the planetary-sized NASCOM network and operated from NASA Goddard in Greenbelt, Maryland. But it turns out there is another giant antenna built in 1960, less than 15 minutes from where I live. It's known as the Stanford dish. Although not quite as large as Goldstone or Parkes, it measures an impressive 46 meters or 150 feet, so it is much larger than the main Apollo MSFN antennas. It is located atop a steep hill above the Stanford campus, along with its smaller sibling. It's in the middle of a spectacular park preserve, and many people enjoy the strenuous walk up to it. This sports activity is locally known as doing the dishes. The large dish is not open to the public, and I always wondered what it was used for. But guess what? The antenna's chief engineer, working for nearby Stanford Research Institute or SRI, watches the channel, and he just reached out to me. He sent me a picture of some old equipment he found at the site. It says Apollo S-band transponder on it, and it has Apollo 15 and Apollo 16 mission badges on it. But nobody still working at SRI remembers what this was all about. So he was wondering if we knew anything about it. And of course, we do. So, after a quick clearance with SRI's management, we were invited for a private visit. Woohoo! What are we going to find? We can't wait. And as you have already noticed, somewhere along the way while I was driving up, my trusty assistant and accidental time travel machine inventor inadvertently bumped my finicky camera into the sepia mode, which transported us instantly into 1960. And officer, I swear I was not even driving 88 miles per hour. How large is that thing?
150 feet across.
It's just humongous.
I'm Steve Muther, and I am a senior research engineer for SRI International. We are the folks who operate and manage this big dish that you see here. The dish was built around 1960, and it was originally a Defense Department kind of thing. It was built on taxpayer dollars. And SRI operates, manages, and maintains it for, well, basically it's a facility for hire. So we get people like NASA, we get universities, we get startup companies. Nowadays, small satellites, CubeSats, seem to be popular right now, and very often we'll get called on to communicate with those In many cases, because they get into orbit and they're unable to communicate with them with their own ground stations because of link problems. Maybe
oh, and then you have the bigger weapon.
Yeah, maybe their antenna didn't deploy properly. We had one of those a few years back. NASA also uses us. We've most recently, I think 2018, we supported the Mars InSight lander mission.
Oh.
They had 2 CubeSats following along with that mission called the Marcos, and I have some information on those inside. And Mars InSight was going to land on the side of Mars which was not Earth facing, and they really wanted to get the telemetry back from the entry, descending, and landing phase, and so they sent these 2 little CubeSats to sort of hold off of Mars, pick up the signal, the telemetry from the lander, and send it back to Earth.
As relays.
As relays, right. And that's a UHF comms link in the the 420, 430 megahertz band.
Really?
Yeah.
Not even S-band?
For the lander, no, not. I think once they get on the ground, they can do the microwave stuff. But so our job was to test those Marco satellites while they were on their way to Mars. And so we uplinked a very strong, with our Klystron amplifier, UHF signal to those birds, and transmitted simulated entry, descent, landing data so that they could fine-tune, maybe fix some software issues, whatever NASA wanted to do.
How much power do you have?
With the old Klystron, I think the tubes are capable of about 30 kilowatts. We were getting between 10 and 12 kilowatts out of it at the time.
Which band?
In the 420 megahertz band.
Okay, so is the whole antenna 420? Because it was equipped for S-band for the Apollo things.
No, the antenna is good for, we have, up there at the business end, right up at the apex, is called the feed horn. And we have a variety of those for different frequency ranges. And so we can support anywhere from about 20 megahertz on up to 2 gigahertz.
Okay, you go really low, huh?
Yeah, really low, and it runs out of steam at about 2 gigahertz because of the wire screen.
Oh, right, yeah, because it's sparse.
Yeah, the rule of thumb is you want the wire screen to be of a size no larger than about 10% of your wavelength.
Right, so it's really S-band is the top of what it can do. For the lower S-band is the top of what it can do. So when it was done in the 1960s, you say it was it was not for radio astronomy, it was a defense thing?
People had the idea that, well, we were going to listen to what the Russians were doing by listening to incidental signals that bounce off the surface of the moon.
Same thing with the large Goldstone antenna.
Yeah.
It's called Mars, so they say, well, it's for Mars communication, but no, it was this military antenna for... Right. So the whole thing was paid for eavesdropping. Yeah. And then used, of course, for satellite stuff afterwards.
So the guys who were around back then are either long retired or no longer with us. And so what I get is stories that, I find on the internet or that have been handed down from, the generation before me. So this has been sort of a learning exercise for me. I've lately been digging into old logbooks recently found and reached out to you and that kind of thing. So.
Yeah, well, we'll see. Do you say you have some Apollo equipment in there?
I do, yeah.
We'll go see that.
All right.
Okay, we have recovered color here, and I didn't see it because of the glare in the camera. But here's the coax. Did you say it was? How big is the coax?
About 5 inches in diameter.
All right.
That's good from our low frequencies on up to about 800 megahertz. And then above that, we've got 2 smaller lengths of coax that are good out to 2 gigahertz.
So before we go in the building, here is a time lapse that Steve took while he was moving the antenna. The building rests on a large bearing taken from an old battleship, and the whole thing rotates with the antenna. There are no slip rings, so you can only rotate so far before you have to unwind it in the other direction to disentangle the wires. How neat is that?
PCB smells so good.
The gray paint and the gray cabinet.
Yep. Well, this is our Klystron transmitter. And most of this is power supply. and it was built in the mid-50s, and I think it was originally built for a medical application, for medical irradiation.
It's a Varian one. It's didn't Varian invent this? A couple
yeah.
A couple of ways. Oh, that's a beautiful control panel. Don't change it. Keep it like this.
You know, it is a museum piece, and I don't think we have any plans to move it anytime soon.
Yeah. Does the scope still work?
You know, I haven't tried it. Most of the electronics in there has been disconnected. It originally had, like, there's a I'll open it up. There's a couple of decks of thyrotrons for pulse modulation, and that's all bypassed. They're wired up for CW nowadays, and I think that scope was for looking at the pulse waveform, so no longer used.
Oh, I see a nice tube back there. Power tubes.
Yeah, I think those are the thyrotrons for the pulse mod.
Over here. Sure. There we go. There we go. I have it. So that's a proper tube. And then the on behind the door there.
Oh yeah. So these are the controls for the focusing magnets. So these adjust focus the beam through the tube. See all the concentric magnets?
Oh, the klystron is this thing.
Yeah.
Oh, I was in front of it. I didn't see
actually,
it.
the active one has all the shielding.
Whoa!
That's the spare.
Oh, and it combines RF magic with magnetic magic.
Yeah. Now the one you're photographing is actually the spare. The one you're standing next to is the one that we typically use. It has all the shielding on it.
Oh, okay, yeah,
we make X-rays in addition to RF.
Yeah, probably.
We can't see anything on that
Those
one.
kind of voltages and currents. Sorry. Yeah.
And so that this is kilowatts of power from the 1960s. It's an original tube?
Yes.
Wow.
I think we even have some spares down in the warehouse.
Looks like it's painted very in red, so that would be my guess.
Yeah.
You know, the high voltage, the anode's up there, and it shoots a beam of electrons down, gets modulated by the input signal, and grows as it travels down the tube, and out comes here. So 5 watts in, up to 30 kW out.
Wow.
And here's a little directional coupler.
I
think that's a 60 dB coupler.
To see if you're transmitting something?
Yeah. And over here we have a switch that'll switch between the two tubes, and another switch that will switch between the line going out of the building and a dummy load.
That's the coax in question. So it's just
center
copper tube inside a bigger copper tube. Oh, it has a little bit of insulation there just to hold it in the middle.
And it's silver plated. Yep.
And that's kind of an expanded version of an N connector, I guess.
Yeah. It's
Mark, did you see the connectors?
That's incredible.
It's a little.
Oh, they're like
Little
miniature.
patch.
Oh, those are cute.
right. So that's our patch panel. One of them. We have 3 in the building.
That's great.
And we have our 2 smaller diameter coax lines coming in heliax from the feed horn. And so with those, we can send it either over to the transmitter room, or we can send it to the front console where we have a receiver.
We were of course wondering what that big motorized wheel was. It's the filament current control.
You can't bring the filaments up all at once, or you'll thermally fracture the actual filament.
It just starts slow and then.
In fact, the motor drive is broken on that. We had to do it manually. So you bring it up a little bit, you'll see an immediate rise in current. You wait till the current falls back as the filament starts to warm up, and then you bring it up a little bit more.
I found historical markings.
Yeah, the old patch panels. And Apollo.
Pioneer. Apollo. And out here.
Yeah.
This is Apollo stuff. Apollo S-band receiver, DSN Stanford interface. And and you have the Apollo 15. Yeah, that's the picture you sent me, right? And the Apollo 16, we figured out that they used it in a moon bounce experiment. It was a weird moon bounce. It was interfering the transponder on the command module with its own reflection on the surface of the moon.
Right.
We had soon figured out from this document that the role of the Stanford dish was for a bistatic radar experiment. That is, a radar where the source is at a different position than the receiver. In this case, the source was Apollo's own transponder. the one we are restoring in the S-band. They also used another source, the transceiver at VHF frequencies that they were using to communicate with the LEM. The Stanford dish was able to receive both the direct signal from the transponder and its reflection from the surface of the moon, and by a combination of RF and radar magic, find information about the surface of the moon. From Steve's research, it is likely that the dish actually did only the VHF radar measurements, not the S-band ones.
So I found evidence that this facility supported both Apollo from 13, 14, 15, and 16.
Oh, okay, all of these.
Yeah, according to the logs.
Uh-huh.
And the NASA document that you sent me may be a little bit misleading about the use of these receivers.
Okay.
These receivers or other ones like them, and these look like they were built here at Stanford. I suspect that these or something like these were sent down to Southern California to the observatory down there.
Goldstone?
Goldstone, yeah. Because most of the log entries that I see, at first I haven't found any log entries that have anything to do with S-band from this site. I see a lot of log entries having to do with the UHF, the 250 megahertz signal. So this facility spent a lot of time looking at that 250 megahertz signal. So this is where you get some of the vintage stuff. Although I think a lot of this is newer than the Apollo era, but you'll notice the old control panel.
Oh, it has the right buttons. It has the twist lights.
And I think back in that day it would have been Nixie tubes. In fact,
Yes.
I found the old Nixie displays. There were ones in there.
LED is no good.
Right.
But definitely those are the right buttons.
What controls the dish now is this computer here, which I believe is a Pentium 2
Yes.
running Windows 98.
Oh.
Why Windows 98? Because it's the last version of Windows that supports DOS. And what do we run on DOS? A little Fortran utility that steers the dish. And really, all it does is take an ASCII file of azimuth, elevation, and time in like 1 second, or in the case of slow moving targets, maybe 15-second or 30-second intervals, and points the dish accordingly.
So you use it as a microcontroller, basically.
And that's it, yeah.
It's just X and Y.
Right.
What do you need
And it gets its timing from the old GPS receiver here.
What have you found?
1971 Apollo.
This is where you find the interesting stuff, because it has the technician's notes, whoever was operating on a given night. And as I was saying, constantly, constantly they were having drive problems. And the PN numbers, those are the Pioneers. So Pioneer 8, Pioneer 9. What they were doing was part of the solar wind experiment. From this site, they were transmitting two signals, a VHF and a UHF, simultaneously harmonically related. They were being received by a receiver on the Pioneer, and in some cases the Mariner. I think both had it. It was used to quantify the solar wind
I see.
and the interplanetary media.
Right. You found evidence of moon bounce in 1965?
July 16th, 1965, moon bounce.
Yeah, still popular today.
Yeah, and I've seen that periodically throughout history. Well, once a month, whether the site's in use or not, I have to kind of go through a routine of checking everything, make sure it all works, just a preventive maintenance. And so what else can you do? Bounce signals off the moon.
So yes, let's not forget, this facility was originally built to eavesdrop on the Russians from moon-bound transmissions. So it's not too surprising that the logbook confirms that the dish was pointed at the moon quite often. So how well does it work? Well, let's say you have a run-of-the-mill 100-watt ham radio, but by sheer coincidence you happen to have a 150-foot dish antenna pointed at the moon. So let's connect the two and see what happens. Yes, that seems to work plenty fine. As every ham radio knows, it's not the size of your radio that matters, it's the size of your antenna. Steve had found some original photographs of the site during construction. Whoa, you can even tell that the dish was originally controlled by a PDP straight 8, so the upgrade to the Pentium 2 was actually massive. Also, you can see that the dish was first assembled flat on the ground before being hoisted up.
So for azimuth and elevation, you have two modes you can operate it in. Rate, which is manual control, like move the antenna with these pots, or program, which is handing it to the computer. The computer's not even on right now, so I'm just going to go to rate, and we'll move the antenna.
Oh, we are rotating!
Yeah, and I can make elevation come down.
And then you see it from over there.
Yeah, sorry about the dirty roof, but there's not a lot we can do about that. Dirty skylight.
It's moving, it's moving. Well, it's moving and we are moving.
Yep.
It's a nice ride. Wow.
Yeah, and once in a while you get little creaks and moans and groans and things when the structure sort of is flexing, but it is pretty good.
That's all you need. And so, yeah, you were joking about your Windows 98 computer, but before that it was a PDP-8.
Right.
And that worked just
right
fine.
In this rack right here, apparently.
Right, that was just fine. It's in the picture back there.
Yeah.
Where is it? PDP-8, straight 8. Well, that was the best slow-mo merry-go-round ride I ever had. Slightly creaky, but very fun. And for the last treat, we got to climb on the giant thing. I felt a little bit queasy up there, and the wind howling in the wires didn't help either. But the views were spectacular, and we could even admire the nearby Stanford campus bell tower. Thank you, Steve and SRI, that was a visit we will not forget. And now, just because, let's have a ragtime antenna dance once again. See you in the next episode.